Hello, this is Mrs. Nearing, and we're going to be going over some problems from Thermo set number 5. And if we look here at problem number 1, we're looking at what is the sign of delta S, the change in entropy, and then predict whether the reaction is going to be spontaneous at all temps, no temps, high temps, or low temps. Okay, so these all are questions about sign. We're not going to have to do any actual calculating here. So first let's look about the sign of delta S. So remember, S is entropy. It is a measure of the disorder. So if things become more disordered, there's a positive delta S. If they become less disordered, then it's a negative delta S. And things we're looking for is number of moles, states of matter. So if we look right here at problem number 1, we'll see that everything's a gas, so that's not affecting entropy. But over on the left, we have 3 moles, and on the right, we have 2 moles of gas. And notice that moles are not conserved during a chemical reaction. Mass is conserved, the number of atoms are conserved, but moles are not necessarily conserved, and this is why there can be a change in entropy. Remember, moles has to do with how the atoms are arranged. They don't have to stay the same throughout a reaction. So we're starting with 3 moles, ending with 2 moles. That means your atoms are less disorganized, so they're kind of stuck into fewer molecules than at the beginning. So we have a decrease in entropy here. So if you decrease moles, you decrease the entropy because they're kind of, you think of them as being like more locked into place, right? So they are less disordered. All right, so that is negative delta S. Let's just go through and do all the S's first. So reaction B, they're all gases, so that's the same, but I'm going from 2 moles on the left to 3 moles on the right. So this is the exact opposite of the previous situation. I'm increasing moles, so it's an increase in entropy. So like over here, I only have 2 things bumping around. Over here, I have 3 things bumping around. There are more possible arrangements of 3 things than 2 things. So the entropy has to do with like how many different ways your substance can be arranged. That's one way to describe like the disorder there in your system. Okay, so C, I'm going, again, they're all gases. And then we're going from 3 to 2. Okay, this is getting repetitive. Okay, so this is similar to problem A, and there is a decreased entropy here, so negative delta S. And then down here, I've got a gas on the left, and I've got a solid and a gas on the right. So in general, solids have less entropy because they're more locked into place, they're more orderly, but I still have a gas on both sides, so that kind of negates that. So let's look at what else is happening. I'm going from 1 mole to 2 moles. So it looks like I have a gas before, I have a gas at the end. All I did is add a mole of a solid. So that is going to add a little bit of disorder. I would guess that this delta S value is probably going to be relatively small, but it is going to be positive because I ended up with more moles than I started with. Okay, now let's look back and figure out, will the reaction be spontaneous? And if someone's asking if the reaction is spontaneous, they're saying, is it thermodynamically favorable? And that means, will the reaction happen on its own without any interference? And in order to figure out if a reaction is spontaneous, we're just looking at the sign of G. So if G is negative, it's spontaneous. If it's positive, it is not spontaneous. And we've got, since we know some stuff about H and S, let's think about how those play out. So we got this equation, delta G equals delta H minus T delta S. In this scenario, H is negative, and T is negative. So it looks like this, you got a negative minus a negative. So that means you basically have a negative value and a positive value, right? So when you add these up, this could sometimes be negative or sometimes be positive, depending on how big these numbers are. In order for the reaction to be, for this to give you a negative G value, we would want the positive number to be low, to be small, right? We would want this number to be smaller than the negative value. So that is more likely to happen when this happens at low temperatures, right? Because temperature is part of that second variable. So if I decrease the temperature, it's going to make that second number smaller, which is going to make G more negative. So this reaction is more likely to occur at low temperatures. Okay, let's think about this next problem. So same equation, delta G equals delta H minus T delta S. the H value is positive and the S value is positive. So again, you've got a positive number minus a positive number. This could be positive or negative, depending on what those numbers are. In this case, in order to get a negative number here, this number will be negative if the second value is large, right? So let's plug in some numbers and come up with a scenario here. So like 10 minus 90 would give you a negative number, right? But if it was 90 minus 10, you'd end up with a positive number. So in order for the g to be negative, we want this second number here to be large. So that's going to happen at high temps. So this reaction is going to be favorable at high temperatures. This reaction is favorable at low temperatures. And again, how do we know it's favorable? We're just asking, like, under what conditions will the delta G be negative? All right, this scenario here, again, if we look at our equation here, you know, delta G equals delta H, which is negative, minus T delta S, which is also negative. So this is just like scenario A. So both values are negative. And so basically you have a negative number, and then negative times a negative, the second number is positive. And in order for G to be negative, you want this number here to be small. So this is going to happen at low temps. And another way you can go about doing this is kind of plugging in some sample numbers, kind of like we did here. So let's test this out. So delta G, if we plug in some, and we know what delta H is, but it doesn't, let's just plug in some random numbers here. Let's just say negative 10 minus, let's say the temperature is 10 and the S value is 10. So let's plug in 10 for everything. Okay. Then if you, the delta G at this temperature would be negative 10 plus 100, you'd end up with a positive delta G value. Okay. If you lower the temperature to 0, okay, you would end up with a negative delta G value. So this tells me that the reaction is more likely to occur, so you're more likely to have a negative delta G when the temperatures are low, right? So we just kind of pick some random numbers, and we could see an example here. At lower temperatures, G is more negative. At higher temperatures, G is more likely to be positive. So this reaction is going to be spontaneous at low temperatures. And if you look at D, I think D is just like B. D and B are the same. In both cases, you have a positive delta H and a positive delta S, and we saw that those would be favorable at high temps. So with problems like this, please don't just try and memorize a list of like negative, negative means low, positive, positive means high, because you're just going to end up memorizing some things you don't really understand what's happening, and then if you make a mistake when you're memorizing, you're going to get it all totally wrong. So what you want to do is just use this equation, which is given to you on the equation sheet. You don't have to memorize it, and you just have to know that spontaneous means G is negative, and then kind of like work through some scenarios like we were just doing here. So try plugging in numbers and say, okay, what would give me a negative G? What would make G positive? Some cases G might always be negative, and that can, no matter what the temperature is. In that case, we'd say it's favorable under all temperatures. So really try and like play around with this equation. Think about the meaning of it. Don't think of it as memorizing a list of rules, because then you won't understand what's happening. All right, so let's look down here at number 2. We've got a reaction. In this case, they tell us what the S is, and we want to explain why it's negative. So you might be asked to predict the sign of S. You might be given a value of S and asked to explain why something's positive or negative. You might also be asked to compare S values for two different reactions and say like maybe why one is bigger than the other. So if we look here in this reaction, what's happening is we've got 3 moles on the left and we've got 2 moles on the right. So we've got a decrease in the number of moles. And we also have a change of state of matter. We're going from a solid and a gas to just a solid. And that's going to cause a pretty big decrease in entropy, because gases are much more disorderly, right? So gases are bumping around. They're really free to arrange themselves in lots of different ways. Whereas when you're in a solid, especially something like this, we've got this ionic solid that's forming a nice organized crystal lattice. There's there's going to be a huge decrease in entropy here, going from a gas to a very structured organized crystal lattice. So we see that S is negative, and it's a pretty relatively large number for S, somewhere in the hundreds of joules. That's relatively large for an S value. Calculate delta G. So there's some different equations for finding delta G. We could use H and S, but we don't know H, so we can't use that equation. So the other equation we could use for delta G is the one that looks like our heats of formation equation. So we're going to use the G of formation of our products minus the G, the sum of the G of formation of our reactants. This is on your equation sheet. It's the one that looks a lot like our heat of formation one. So our products, I've got 2 calcium oxides, 2 pure calciums, 2 oxygens. And you will notice that just like with heats of formation, whoops, I put that number in the wrong spot. Just like for heats of formation, the delta G for something that is already in its elemental state is going to be, whoops, there shouldn't be 2 there. The delta G for something in its elemental state is going to be 0, because the delta G describes the free energy change, kind of like your heat of formation. It's the energy change involved in forming 1 mole of something from its elements in their elemental state. So if the thing is already in its elemental state, then whoops, that was just a 0. Then their delta G is 0. Okay, so anyway, so it's products minus reactants. In this case, it's the only one that has a number is products. This is relatively straightforward. So you end up with negative 1206.6. The units here are in kilojoules. And calculate delta H at 25 degrees Celsius. So there's lots of ways to find delta H. Remember, we can use calorimetry, we can use Hess's law, we can use heats of formation. There's all sorts of equations. Which one you use depends on what you're given. So what we know here, we know that the delta S is negative 364.6 joules per Kelvin, and we know that the delta G is negative 1206. So it looks like we want to use this equation right here, delta G equals delta H minus T delta S. So I'm going to rearrange this. Delta H, let's see, equals delta G plus T delta S. And if I plug that in here, my delta G is negative 1206 kilojoules. Whenever you are doing this equation, pay attention to units. So notice how your G is in kilojoules, your S is in joules. So you want to convert the joules into kilojoules. This is negative 0.364 kilojoules per Kelvin. And since this is in Kelvin, I need to convert my Celsius temperature into Kelvin. So I end up with negative 1314 kilojoules. And remember, this is a delta H that we just calculated, so this is a exothermic reaction. So negative delta H, it lost energy, gave it off to the surroundings. Is this reaction driven by enthalpy or entropy? So when we talk about what drives the reaction, we're saying like what makes it spontaneous. So what makes it if you're asking what makes it spontaneous, we're basically saying what makes delta G negative. That's the thing that's going to make this reaction spontaneous. So delta G is delta H minus T delta S. We can see that our delta H value is negative and our delta S value is also negative. So when the reaction is spontaneous, that means G is negative. That is going to be happening because of this negative H value, right? This is the thing that's going to help make G negative. Having S be negative, that is not very helpful, because if subtracting a negative is going to make this number more positive. So the negative delta H is what makes the G negative. So we would say that this is enthalpy driven. It is the H value that is allowing this reaction to be spontaneous. Another way to think about it is you can just say things being exothermic tend to be spontaneous, or things that increase in entropy tend to be spontaneous. And this reaction is decreasing in entropy. That kind of goes against the spontaneous way of things. So what must be allowing this reaction to happen is the fact that it's exothermic, that it's got a negative delta H value. So yeah, again, this whole, like, whether a reaction occur all comes back to, is